Caltech just made silicon chips guide light almost like optical fiber. Imagine if the tiny silicon chips inside computers could guide light with almost the same efficiency as the optical fibers carrying information across the internet. That is essentially what researchers at the California Institute of Technology have been working toward, and their latest breakthrough could have major consequences for the future of computing, artificial intelligence, precision sensing, lasers, and even quantum technology. Caltech scientists have developed a new way to create extremely low-loss optical pathways directly on silicon wafers, with performance approaching that of optical fiber at visible wavelengths. The achievement is especially important because moving information with light can be far more efficient than moving huge amounts of data using conventional electrical signals, but light normally loses some of its energy as it travels. Through a material, doubt. The researchers have now developed a platform designed to dramatically reduce those losses, potentially allowing sophisticated optical systems to become smaller, more efficient, and easier to integrate directly onto computer chips. Optical fiber has become one of the most important technologies supporting modern civilization. Every time enormous amounts of information travel between cities, countries, data centers, and communication networks, optical fibers carry much of that information as pulses of light. Their extraordinary performance comes partly from the purity of the glass and the smoothness of the optical pathway. When light travels through the fiber, relatively little of it is absorbed or scattered, allowing signals to travel enormous distances while retaining their information. Reproducing that kind of low-loss performance on a semiconductor chip, however, has been extremely difficult. A computer chip may be only centimeters across, but researchers want light to travel through its optical circuits many times, sometimes effectively covering distances of meters or even kilometers as it circulates through tiny resonators. Every tiny amount of loss can accumulate, reducing the performance of the device. Caltech's approach tackles this problem by bringing a material similar to the glass used in optical fiber directly onto the silicon wafer. The key material is called germano-silicate, a type of glass used in optical fiber. Instead of manufacturing a traditional fiber and then connecting it to a chip, the researchers adapted this material so that it could be patterned using semiconductor manufacturing techniques. They create nanoscale structures called waveguides, which act like miniature roads for light. But these roads don't simply run in straight lines across the chip. The researchers arranged them into tightly packed spirals, allowing light to travel through a much longer optical path while occupying a tiny physical area. The concept is similar to winding kilometers of optical fiber around a spool, except nanofabrication allows that optical pathway to be compressed into a chip measuring only a few centimeters across. This gives researchers access to the benefits of extremely long optical paths without needing physically enormous devices. One of the biggest breakthroughs appears at visible wavelengths. Existing photonic technologies often rely on materials such as silicon-nitride because they can guide light with relatively low losses. But visible light has presented a particularly difficult challenge for integrated photonics. Caltech's new germano-silicate platform substantially improves performance in this region of the spectrum. According to the researchers, their system has achieved a 20-fold improvement over the previous silicon-nitride record at visible wavelengths. The secret is an unusual manufacturing step. Because the material has a comparatively low melting temperature, researchers can heat the waveguides in a furnace and allow their surfaces to effectively reflow. This process makes the optical surfaces extraordinarily smooth, down to a level approaching individual atoms. That smoothness is crucial because microscopic imperfections can scatter light, causing signal loss. By reducing those imperfections, the researchers can dramatically suppress scattering and allow light to remain confined within the optical pathway for much longer. The improvement becomes even more interesting when lasers are built using these low-loss optical structures. According to the researchers, lasers produced using the new platform demonstrate more than a 100-fold improvement in how long their light remains coherent compared with previous designs. Coherence is extremely important because it describes how consistently the electromagnetic waves maintain their phase relationship. Highly coherent light is valuable for precision measurements, advanced sensors, optical communications, and many quantum technologies. The researchers explain that every 10-fold reduction in optical loss can produce roughly a 100-fold improvement in coherence for lasers relying on these resonant structures. So reducing what may seem like a tiny amount of optical loss can create a surprisingly large improvement in the performance of the entire system. That is why the researchers are interested in applications far beyond conventional communications. One possibility is the development of extremely precise optical clocks. These devices can measure time with extraordinary accuracy and are important for scientific experiments, navigation, telecommunications, and fundamental physics. The expanded wavelength range could also help create miniature atomic sensors and optical gyroscopes capable of detecting rotation with extreme precision. In quantum technology, low-loss optical pathways could provide new ways to manipulate and control light at the chip scale. And in artificial intelligence data centers, where enormous quantities of information constantly move between processors, memory, and networking hardware, replacing some electrical connections with efficient optical pathways could potentially reduce energy consumption and improve communication performance. The idea of achieving fiber-like performance on a chip may sound strange because the chip itself is so small. Why would researchers care about optical losses measured over meters or even kilometers when the physical device may be only 2 centimeters wide? The answer is that light can circulate repeatedly inside optical resonators. Consider a tiny ring-shaped waveguide. Light enters the ring and continues traveling around it again and again. If the pathway is extremely low loss, the light can survive for a very long time, effectively traveling a huge distance, even though the physical ring itself is only a few millimeters across. Each additional circuit can strengthen specific optical frequencies and improve the performance of lasers and other photonic devices. The less energy the light loses on every trip around the ring, the longer it can circulate, and the more powerful the resulting optical effects can become. The researchers have already demonstrated several different components using their new material platform, including ring resonators, multiple types of lasers, and nonlinear resonators capable of generating different optical frequencies. This versatility is one of the reasons the Caltech team describes the technology as having a kind of Swiss Army knife quality. Instead of being useful for only one specialized application, the same low-loss platform could potentially support many different photonic technologies. And because the structures can be manufactured directly on the same large silicon wafers used in semiconductor production, the approach could eventually be compatible with scalable chip manufacturing. That could be particularly important if photonic systems are to move from specialized laboratory equipment into mass-produced technologies. There is still a significant amount of work ahead. The researchers describe the current achievement as an important step rather than the final version of the technology. Manufacturing, integration, scaling, packaging on